ओके, ठीक है,
आप
ठीक है,
स्टार्ट
ठीक
कर
है, ठीक है। Is it live now? Sanjeev, is it live?
Yes, sir. We are
Okay,
live.
so we can start. We can start, right? Okay, so good evening and welcome to this interaction session for this NPTEL course on ideal fluid flows using complex analysis. So we kept this session to see if you have any questions, which I can answer maybe on the spot. And then also we received a few questions when the request was sent earlier. So we can try and answer those questions as well in this session. So if you have any questions, please feel free to type them in, and then we will try and take up as many questions as we can in this session. Okay. So let's get the topic started. Let me say a few words about the course now that I think you're almost towards the end in this course. It's a 4 week course, as you know. So we started on a very simple topics. In fact, just getting the basics covered up, which you have come across, especially the concept of the velocity, potential, and stream function that we very often do in first year fluid mechanics, or rather first course on fluid mechanics. But then the from starting from the second week, when or rather towards the end of the first week and the beginning of the second week, we started looking at things from the perspective of complex variables. So that is where the tempo basically shifts in this course, and from there on, it's all about using complex numbers to be able to compute uh, different flows using superposition. Of course, we first started with some very elementary flows, which are just standalone flows, which do not require superposition, such as source and sink, okay, vortex, which are flows which happen, which are just on their own. There is no idea, there's nothing to superpose, and even uniform flow, by the way. But then from there on, we moved on to adding flows and creating more complex solutions, which otherwise using regular analytical methods would be very, very difficult to work out. So that was how the second week went by, and then the third week basically brings us to more detailed superposition flows, and then we started talking about calculation of forces. We looked at flow past a cylinder, with circulation, without circulation, and there uh, we looked at even flow past a Rankine body, which was a half Rankine solid. And then finally, the fourth week, when you see now, would actually have details on calculation of forces. So once you have the flow, we are more interested in knowing what kind of forces do you would a body experience when it sort of when it is exposed to this flow, when you have the fluid flowing past a body, and so the flow is known, the fluid velocity is known, but we want to calculate how much force that body will see, okay, or would feel. So basically that force then comes in, is required because you want to build fixtures to hold those bodies, right? Or if you're designing an aircraft, you need to calculate how much drag this machine, this plane will, let's say, will experience, so that you can accordingly decide the size of the engine or the power required for maintaining a certain velocity. So we this is basically in a nutshell the entire course. So I'll just quickly talk about two questions that came as part of the online, the Google form that we circulated. So the first, or let me take the second question first, which is a more interesting question. And the question is about, the question says that other than viscosity, is there any other factor that can influence the rotationality of fluid dynamics, or rather fluid elements? So the question talks about which factor uh, produces rotationality or rotation in a fluid. Uh, so it is actually, the answer is already there in the question. I mean, it is viscosity, which basically creates rotation. In fact, if there was no viscosity, there would be no. So let me talk about the physics of rotation. Why do we get rotation in a flow? Now, typically, what happens is that you have, if you have a solid object, which is, let's say it's moving with some velocity. So the fluid surrounding it would basically get, it's a real, if it's a real fluid, we talk about any fluid such as air or let's say water, the two most common fluids that we encounter in practice, that fluid would sort of attain the same velocity on the surface. It's the fluid particle would want to move with the same velocity as the velocity of the solid, and that is what we call as the no slip boundary condition. Now that no slip, essentially what it does is, because the fluid touching the solid goes with the velocity of the solid, the fluid next to that, the next layer, in the fluid sort of moves slowly. It has viscosity that comes into the play, so it basically moves a little slow. It is slow to respond. And the fluid in the next layer would be even slower. So typically we get, as you know, in fluid mechanics that you would have studied in your undergraduate curriculum, we get what is called as shear. We get a shear force on the surface. Now this shear force is what creates a velocity gradient. So to say, let's say it could be, du. Let's say if it's x component, so du dy plus maybe du dx of that type. So the shear component introduces a velocity differential above the solid, and that velocity differential is what creates rotation. In fact, vorticity, the key component in all of rotational fluid mechanics, is actually created only at the interface of a fluid and a solid. It is at the interface of a fluid and solid where vorticity gets generated. If there was no such interface, you may not even see vorticity, which is typically the case. We took an example, I think I mentioned in one of the lectures, that if you have flow past a solid, and you have a development of a boundary layer on that solid, far away from the solid, you still have irrotational flow, even though the fluid has finite viscosity. Okay, but even though the fluid is is not an ideal fluid in that sense, because the viscosity is not zero, far away the flow becomes irrotational, because there is no shear in that region. It's the fluid element is not able to turn around on itself. Okay, so vorticity plays a key role right at the interface of a solid and a fluid. So rotationality in that sense comes from the dissimilar nature of properties between when the solid and the fluid meet each other. Now, going from there, the second question that we got, which is slightly open-ended, but I will try and answer this. It says, can you please suggest a good research paper which makes use of the topics covered in this course? So I would say, if you want to look at good research papers, you'll have to go for very classical papers. You can pick up papers from the time when Ludwig Prandtl was developing some of the ideas that we have discussed. You could look at, so these are from the early 20th century, I would say, the classical papers that where you would see a lot of uh, concepts that we have covered. Uh, if you want to look at textbooks, I would say, where more of this can be found, you can pick any generic textbook on fluid mechanics. Some of the good ones are, there is a book by which I have also referred for this course, or two books which I have referred for this course. One is by Curry, by IG Curry, which is where most of the material that I have taught in this course comes from. And it has some very nice examples of how complex flows, especially for different shaped airfoils, were recreated using complex analysis. So Curry is a good book. There's another book by Kundu and Cohen. That's also a very good book, which has some aspects of how design can be done uh, based on potential flows, I would say. But it doesn't go into complex analysis, but it uses potential flows in general the way it is taught in maybe undergraduate curriculums. But the book by Curry is a very good source. It's a very classical book. It's a very old book, by the way, but it's a very good book which has a lot of details and many nice and interesting problems that you can solve in case you want to know, you want to gain a certain bit of expertise on how this on how the ideas that we've covered in this course, how they can be applied in practice. So there are some good case studies there, so which you can look at. So these are the two questions that we received so far, and maybe Sandeep or Sanjeev, you can let me know if there is any question on the chat which we can take up.
No, sir, there is no question as of now.
Okay, maybe we can wait for a minute and then maybe carry on the
Yes, sir.
discussion from there. Maybe what I'll do is I'll just quickly elaborate on the part that I was mentioning about vorticity at the wall. Let me see if I can share my screen and say some things about this. Yeah. Is my screen visible? Sanjeev?
Sir, it has changed, but it's still loading. It's not visible actually.
Okay, okay. Let me know when you see the black screen.
Yeah, it's fine now. It's visible.
Fine now. Okay, so what I was saying is, let's take the simplest case that we cover many times in fluid mechanics, in undergraduate fluid mechanics, which is maybe flow over a flat surface. Okay, a flat solid, so flat plate, and you have some flow coming over this plate. Okay, so let's say the flow comes at velocity u, and let's say it's a real fluid which has some viscosity, and the surface is stationary. Okay, so what we expect in this case is that, see, if the surface was not there, this flow will go, from left to right without any change. You will see the same profile, right? It will just pass through. But since there is a solid, the fluid will actually now slow down, and what the profile that you would get, which we typically define as a boundary layer, would be of this type, right? There would be a velocity profile within this boundary layer, which would grow in that fashion, right? So the velocity will gradually increase until you get stream velocity. Okay. So here we'll say u is a function of y, where y is this coordinate, and we have x, okay, along that direction. Okay. So what I was saying about shear is that now, because the flow goes over the solid, you have a velocity gradient at the surface. So in this point, du dy is not zero. Is not zero. Okay, there's a shear that is created. And so if I assume the fluid to be Newtonian, I would typically write tau xy to be mu du dy at, in this case, y equal to 0, because I fixed the y coordinate in a certain way. So y0 is basically the surface of the solid. Okay, so this is non-zero. This shear is non-zero. There's a non-zero shear that the fluid will experience. Okay, that's a friction, basically, the friction that you get from the wall. Now, the vorticity in this case would be dv dx minus du dy. All right. If I consider the flow before the plate, if I consider flow to the left of this plate, okay, everywhere in this region, okay, here v is 0, the v is the y component of velocity, and u is capital U, okay, which means omega, which is dv dx, which is 0, and du dy, u is constant u, so this is 0. So omega here is 0 in this region. There's no vorticity. But right when the flow hits the plate and you have a boundary layer that develops, so even though on this, so look at this plate now, if I look at this point only, this point where we are stationed, maybe at some x, this is some distance x from the leading edge. Okay, so say this is some distance x. So at this location, dv dx, so around this point, if I move along this surface, if I move along, if I, just one second, if I move along this surface, along this direction, right, just if I take a small element in this direction, dv dx is 0, because the velocity v is still 0. It's 0 everywhere on this plate. So dv dx is 0, but du dy, there's a change in velocity, sudden change in velocity, right? It goes from 0 to something else. So this is not 0. And so omega is not equal to 0. There's a finite du dy. So vorticity is not 0. So what we have done is, so we had an irrotational flow coming in. The presence of this boundary creates a rotational flow. Okay, so you get a non-zero omega that is created. So that is the reason I was saying that when you have these situations, rotationality comes because there is shear, right? There's a fluid friction force that is created, which you typically will not see in the irrotation flows, right? If you have an ideal fluid which has zero, which has mu to be 0 or zero viscosity, you won't see this problem, because there on the boundary, the fluid can slide on the surface. It doesn't have to match the zero slip condition along the tangential line, which I covered in the first lecture, I think, of this course, that u dot t need not be 0, but u dot n has to be 0. Okay, but when you have a real fluid with non-zero viscosity, both conditions, u dot t and u dot n, both have to be satisfied. So that is how we get rotationality. Okay. Yeah, anyway, Sanjeev, now if there is any question.
No, sir, not yet.
Okay. Okay. Let me see. So I've discussed what we did in the course. If I can maybe look at some critical parts, which, oh yeah. So this is one part that maybe I can just emphasize again, which I believe might have been new for this course, which is not taught in the undergraduate fluid mechanics. I mentioned one thing, that if you have two lines, let's say you have psi equal to constant line and phi equal to constant line, right? Psi is a stream function. And phi is the velocity potential. So when you look at these lines, so maybe psi constant line is this line, maybe psi is C1. So the lines of constant isopotential, or the lines of constant potential, I should say, constant phi, will always be perpendicular to these lines. So you will have phi, maybe some value, I don't know, maybe say maybe K1, which is 90 degrees here. Then you have phi K2, 90 here, maybe phi K3, and so forth. Phi K4. So essentially these two functions, when you draw their lines, they would always be at 90 degree to each other in irrotation flows. Now, what we did with using this is that in many places, in fact, the whole idea of constructing the complex potential f of z. I wrote f of as phi plus I psi. Okay, the whole purpose of doing that was because these two are actually orthogonal functions. So if you write z, for instance, as x plus iy, note that these two coordinates are also orthogonal to each other. In the z plane, x is here, y is here. So these two are always orthogonal to each other. Similarly, f of z, which is a combination of two orthogonal functions, phi plus I psi, so they're also orthogonal to each other. So this is something that we have used in this course quite extensively, which is a new thing, which I'm sure is a new concept, which may not be very apparent. Why we did this, but the basis is because they are, by making them orthogonal, it actually becomes easier for me to, or for anyone to be able to satisfy or to ensure that the Cauchy-Riemann equations are satisfied for this selection of f of z. Okay, right? So as long as the Cauchy-Riemann equations are satisfied, that means that the function is analytic. We can start working with the tools that we have developed in this course. Okay, and remember the Cauchy-Riemann equation that we developed for this f of z are very nice. They say that u, which happens to be d phi dx, is also d psi dy, and v, which happens to be d phi dy, is also minus d psi dx. Right? Because we note that u and v would satisfy the continuity equation, which is du dx plus dv dy to be 0. Right? That gives me this equation. Continuity gives me the definition of psi. Okay, and irrotationality gives me the definition of phi, because we said u vector is gradient of phi as del cross u is 0. The flow is irrotational, so the curl of velocity is 0. So u has to be the gradient of a scalar function, right? So when I write this, u is gradient of phi, I essentially say that u is d phi dx and v is d phi dy, right? So we get that dependence. So we exploit this fact here, that so the two equations that we really need to be able to write f of z, the complex potential, are these equations in fluid mechanics. We need the continuity equation, and then we need the condition for irrotationality. These two equations actually form the backbone for everything that we have done in this course, in fact. Okay. So that was about the two functions being orthogonal to each other.
Sir, we have a question on this.
Yeah.
Yes, the question is from Mahadev Prabhu. He is asking like whether this orthogonality condition of phi and psi lines are valid even for stagnation points.
For
Stagnation points.
stagnation points. Okay, that's an interesting question actually. Let me put it this way. It is valid for stagnation points, except stagnation points are very special points. Okay, stagnation points are points where actually, let me put it this way, that the function, the slope of the function, let's say at a stagnation point, typically you will get a stagnation point is defined as one where the two components of velocity will go to 0. So at a stagnation point, actually, if you just plot the stream function or the velocity potential, that function should have 0 slope from all directions. Whichever way you approach that point, you should get a 0 slope. So, and the function also tends to be, in that sense, I don't want to call it as multi-valued, but it can have bifurcations basically. So if you look at maybe flow past a cylinder, right? Let me maybe draw that one. So we take a flow past a circular cylinder and say without circulation. So we know that otherwise the flow would look like that, right? The flow would go like this, but there is a dividing streamline. So there is a stagnation point here and this is stagnation point here. Maybe I don't know if I can mark it here. This is point A and there is point B. These are two stagnation points in this flow. All right. But if you look at the streamline corresponding to these two stagnation points, this is actually this streamline. So the streamline comes here straight. That's the same streamline, and then it bifurcates on both sides. Okay. So at this point, point A, and similarly at point B, the same thing will happen. Okay. At this point, the function psi is also changing its nature. It's the only thing is that its slope from all directions is going to be zero because the velocity there is zero. So it is true for what you said that the two functions are orthogonal. It is also true for stagnation points, except at a stagnation point, the situation from a visual perspective may not appear that the two functions are orthogonal, but they are actually orthogonal because the function can bifurcate into many segments. Sanjeev, any other question now?
No, sir.
Okay. Maybe can I take? Let me see. Yeah, let me just look at cover some very some important aspects about the way we have worked out this course. Because I want you to be able to write this at all times. So remember, our objective in fluid mechanics is always to get the velocity and pressure. So I've been writing velocity as W of Z, right? That is a complex velocity. Okay. So W of Z, if you're writing in Cartesian coordinates, you would write this as U minus IV, not U plus IV. That is one thing that you have to remember, that there's a reason why there's a negative sign there. Okay. And if you are writing WZ in cylindrical coordinates or in polar coordinates, you would write this as UR minus IU theta into e to the power minus iota theta. Okay. And these are interchangeable, by the way. This is the same velocity. You can interchange between the two, whichever, if a problem has circular symmetry, some form of symmetry, circular symmetry, then it makes sense to use the cylindrical coordinates. But if it doesn't seem to show a symmetry, and you learn with experience that if it doesn't make any sense, if the problem becomes harder to solve if you use cylindrical coordinates because there is no symmetry, then it makes sense to use just plain old Cartesian coordinates or Cartesian system. So typically problems where you have circular geometries or angular symmetries, there we should always go with cylindrical coordinates. But even if you work it out with the Cartesian coordinates, it's just that the answer may take some time to, you may take some time to reach there, but it should be possible to solve it. It is not going to be something which cannot be worked out. Okay. So that is one thing. The second thing that I wanted to mention is let me see. So no. Yeah, the second thing I wanted to mention is about when you write these complex potentials. In most problems that or the most analysis theory that I developed in the course, I have assumed that singularity is located at the origin. Okay, but to break out of that that trap, I also solved two problems which are available on the same course page, where I have taken a few cases where singularities are not at the origin. So for instance, we wrote that if you have a source at the origin, okay, so this is origin in the xy plane on the z plane. So I said if you have a source of strength plus m at the origin, then the complex potential is just m by 2 pi log of z, right? But the thing that you need to remember at all times is that the source may not be at the origin, or the origin may have been translated. So in case if the source happened to be maybe at some location, say, I don't know, z naught, so the source was right here, then you should know that the function complex potential would be m by 2 pi log of z minus z naught. So basically you translate the coordinate system to that point, right? So if I have to go from this point to this point, I would just do a linear transformation of the entire coordinate system, so that the singularity then happens at that point. Okay, when you put z to be z naught. So it is that idea. So you need to remember that the coordinate where the singularity is located is very important. So in the original case, we had the function to be z minus 0 actually. But now we have z minus z naught because z naught is the point where the singularity is located. Same thing happens even when you do vortices, free vortex or sinks. The same thing will apply. Okay. Sanjeev, any other question?
No, sir.
Okay. So that is one that you need to, again, as I'm saying, you need to remember this because you may see some of these questions in your assignments and maybe in the exam. Let's see. Yeah. The other thing is, well, source and sink are easy. If a source has a potential of this type, a sink just requires you to put a negative sign here, right? So negative sign for sinks, right? You just put a negative there and you get the complex potential for a sink. It gets interesting when you have a vortex, right? So let's say you have a vortex of strength gamma, which is in this case, it is say clockwise, right? So clockwise gamma will give you a complex potential, which would be I gamma by 2 pi, and say this is at some position, I don't know, maybe z1. Okay, so I gamma by 2 pi log of z minus z1. Right? That becomes the complex potential for vortex located at point z1. And if it was a maybe a counterclockwise vortex, maybe somewhere here, okay, gamma at maybe point z2, then we'll have f of z to be minus I gamma by 2 pi log of z minus z2. Okay. So in both cases, singularity has been shifted, and more importantly, unlike the case of you know source and sink, where an iota is missing here, there's an iota which appears here, and it changes from plus I to minus I depending on which rotation you are considering. If it's clockwise rotation, then you take a positive. If it's anti-clockwise rotation, you take a negative. Okay, so we did this in the course, and I showed with arguments why this has to be plus or minus. Okay, so that was actually something that you should remember, and it's easy to remember, by the way, these things. It's just four things that you have to remember in the course to be able to solve every problem that you encounter. So I hope that this part you can sort of uh, commit to your memory. Let's see anything else that was of interest. Um, so one of the things that I really like about this course is that we are able to derive the flow pattern for flow past a cylinder with both circulation, without circulation, and with circulation. So I hope that that part is clear, because that requires you to first develop what is called as a doublet. Okay, so my own undergraduate experience has been that doublet is a hard potential to understand. Okay, but the complex analysis actually gives you a very clean form of deriving the doublet. So I hope that was clear, and then so you could see how flow past a cylinder comes out naturally when you have a doublet with a uniform flow, and you can derive the pressure distribution and the velocity distribution quite easily without having to resort to much more complicated tools. So that is one thing that we have done. Um, the other thing that uh, let me see, that we did was, one more thing is about how do we calculate stagnation points for flow in for typical flow patterns. And I took examples of flow past a cylinder again to emphasize what are the stagnation points, how do you derive stagnation points. So that question anyway, that is partly answered in in the earlier question that was asked, but still. um, then let me see. I did some demonstration exercises, by the way. For example, the flow past a Rankine body, a half Rankine body, was actually which is superposition of source and a uniform flow. It basically is required because or it emphasizes the same aspects, that when you have these kinds of superpositions, you get different bodies which can be formed. So right, so when you get a dividing streamline, you can always slide in a solid, or consider that a solid can be put in there in place of the streamline, and then you get, suddenly you have a flow pattern around some object that you are physically modeling. Remember, this is all modeling. It is not that this is how the flow will happen, but we model the situation. So the modeling part is what we covered in this course. And uh, except the problem solving sessions which we did, uh, yeah, the forces part, if I don't know if anybody has seen those lectures yet, but if you want, you can maybe ask any question on how do we calculate forces. But the forces part, we looked at Blasier's theorem that you would see in the last week. Okay, where we calculated the complex force, or the form of the complex force. Okay, so that is based on the pressure distribution on the solid. So I hope that when you see that, maybe, or if you've seen it, that part would have been clear. Okay. And then we took a demonstration exercise, by the way. Again, we did one thing where we said we have already calculated, we know the force on a cylinder when you have superposition of three elementary flows. So we tried to derive the same expression, the same force, using the Blasier's theorem, which requires us to go and rely on the residue theorem in complex analysis, right? So we look at calculating residues where the singularities exist, and we got the same answer there as well. So the drag is zero, and the lift is sort of like rho u gamma, or it's proportional to the velocity and the circulation. So that is what is called as a Kutta-Zukowski theorem, a very fundamental theorem in all of fluid mechanics. In fact, that was the basis by which much of aircraft design happened. Okay, that how much lift can you get? So depending on the pattern, the superposition of these elementary flows, you could decide how much lift the wing will give you. So that is how the wings were designed originally. Okay. The last topic that we covered in this course was on conformal transformations. So I don't know whether anyone has seen this, but conformal transformations are basically now extending what we have learned as simple flows, extending those to complicated bodies, complicated shapes. So it's some form of transformation, coordinate transformation. So you transform a simple shape into a more complex shape, or you go from a complex shape to a simpler shape, or vice versa. So those, I've taken some examples in the last lecture. I considered a couple of cases where conformal transformations have been used to create flows for some very nice shapes using what we have learned otherwise. Okay, so I hope that would also be clear. If anybody has any question on it, please feel free to write it on the chat. Otherwise, yeah, that is the last part that we have covered in this course.
Sir, we have a question.
Huh.
Okay, so again, this is from Mahadev Prabhu. He's asking, a free vortex is characterized by its strength, that is gamma by 2 pi. A non-zero circulation means a non-zero vorticity. Now, how can I say free vortex is irrotational?
No. A non-zero vortex
Circulation.
circulation.
A non-zero circulation means a non-zero vorticity. Now, how can I say free vortex is irrotational?
No. So I think, yeah, that's a good point. If I understand the question, it's a long one, but let me see if I can answer this in the right way. So what he's saying is this: if you take a free vortex, let me take the free vortex and put it on the origin just for convenience. Okay. So I think what he's saying, and we can take any rotation, let's take it clockwise rotation. Okay. So let's say this is gamma. And so the flow that you would see in this case would be, sorry, the flow that you would see would have velocities of this type, right? So I can draw the arrow here. So the flow would go in circles. Okay? Something of that type. And then you can draw more, it doesn't matter. Now the question that he is asking is that even though there is rotation, why is the flow still irrotational? I think that's what I understand. I think that is the question. That there is rotation. We're saying there is rotation because of course the fluid element is going round and round, but then we are saying it has no vorticity. So it's a very good point. Actually, the answer to this would lie. Let me say answer it in the easiest possible way. Say I take a contour, and you can take any contour, by the way. That is the best part. Let me suggest a contour of this type, which is easy to evaluate. For testing what I'm saying. Say I take a contour of this type. Let me just draw this again. Yeah. So let's say I take a contour which goes like this. So you go in this direction. In this contour, you maybe branch off along the x-axis and then you turn around. Okay. And then you come down. So maybe the contour is this contour. Let's say this is contour C. Okay. Which encloses this region. But it doesn't enclose the origin. That is this key part. Okay. So I know the velocity on this contour and I know the velocity is parallel to two layers on this contour. So remember the velocity here, there is only u theta in this flow. Okay, there is u theta which is not equal to 0, but ur is 0 in a free vortex. There's no radial flow, there's only tangential flow. So if I look at the four segments in this contour, let's say I said this is segment 1, this line, then we have segment 2, segment 3 and segment 4. We have this contour C comprises 4 segments. So when I have to calculate u theta, or let me not put u theta, let's say u dot integral, when I want to do u dot dl, where L is the variable along this contour. L is the incremental length along this contour and we do a contour integration. Okay, we go all around the contour. You should be able to prove this to yourself that this will be 0. Okay, and this is gamma, by the way, the circulation for this problem or for this flow. The reason this comes out to be 0, even though there is flow, is something that I want you to discover on your own. And I said this contour should be one which does not enclose the origin. So it could be maybe very close to the origin as well. You could take a contour maybe which, let me take a new one, say maybe of this type. I go almost near the origin, then I turn around, I go here, I turn around, something like this. Or you could take any irregular contour which doesn't include the origin. For all these contours, this will be true. U dot dl will be 0. Okay, I took a the curvilinear one, that specifically because it's easy to evaluate that, because in this case u and dl become u theta and dl become parallel to each other. Okay, dl is a arc, is a length along that arc, and u is just u theta. So you can evaluate this and see that this is 0. So gamma is 0. That means that the flow is actually, in this case, I mean, this is circulation around that loop. It basically means that there is no vorticity contained within that contour C. Okay, gamma, when we say gamma is 0, it means there is no vorticity within that region of space. And that is the reason I'm saying that there is no vorticity. So it's, the flow is still irrotational. It is not rotational. The singularity appears at the origin, which is where you have a source for creating this circulation. So that is not counted. We always branch off. In complex analysis, when we have a singularity, we sort of branch around it. We never go to the singularity. Okay. So this is the reason I said omega is still 0. And so the flow is irrotational and there is no problem. You should try this actually. If you can, take this kind of a contour, which is aligned to the, in a certain way. The alignment basically is that the distance from the origin on this contour 2 it remains same, say R1, and the distance from here to here remains, let's say, R2 always. So these are circular arcs. Okay, so what would happen is that you will have dot product along the path 2 and along path 4. Along path 1, u dot dl will be 0 because u is normal at that point. Okay, there's only u theta at this point. So u theta will have this component here, which would be normal to dl. So on this, if I take a small element here and maybe exaggerate here, right? So this is dl vector. So this is going in this direction, but u theta, or rather u vector, would be normal here. So u dot dl will be 0 along paths 1 and 3. So they won't contribute anything. The only place where you will get contribution is along path 2 and 4, and they would be equal and opposite. So they will cancel off. So that we have done. Actually, you can try and prove that to yourself, and maybe you'll be pleasantly surprised that why this happens. So that is the answer to this question, that the vorticity remains 0. Any other questions, Sanjeev?
No, sir.
Okay, so I have actually described pretty much everything that we have done in this course, sort of just as a summary. So if there are any other questions, please feel free to share with us on the forum. I or the TA will try and answer those questions, as we've been doing. We received some questions, we did answer. So I hope the answers were satisfactory, and you were able to get some understanding of, what our perspective is on those aspects. But it's still on. If you want to send any other questions, we'll be happy to answer them. Okay. So if there are no other questions, maybe we can end this session. Sandeep, are you there? Can we end the session then?
Yes, sir.
Okay.
Yes, sir. We can.
ठीक है,
end, sir.
ठीक है. Okay. So thank you all for joining and asking questions, and
Yes, sir.
yeah, we look forward to for any more questions that you may have. Please, as I said, do email them to us. We'll try and answer, okay, as much as quickly as we can. Okay, and best of luck. I hope you're enjoying the course, and it has been helpful for you. I hope that that was a whole motivation for us to give you the same ideas but using a different approach, which I feel may look intimidating, in the early part, but once you get the hang of it, this becomes much easier to be able to implement. Okay, so thank you, and yeah, have a good evening then. Thanks. Bye.